Swayam Prabha. Digital India. Educated India.
The basic idea, so what we have done till now is, of course, we have looked at first law, second law. The second law gave us the idea of availability. And to very quickly recall, we said that not all energy is available. And we found out from a control volume how much work is possible. We wrote down an expression for that, with what is given here. And we found the irreversibility which is there. And of course, this is the general expression that we have. I have added this slide, which was not there earlier, just to the form these conditions. And of course, the third condition is this condition here, the uniform states. This is uniform state, this is steady state, and this is control mass or closed system. And of course, this is a general expression that we have. Of course, these are the three special cases that we consider. And we know that from this general case, we should be able to drive all of them. So I've given you all these expressions for your ready reference. And of course, as I said, that you can write down, you cannot print these slides, okay? And there's a down, because when you write it down, some amount of additional thinking and learning that can happen. Okay, so there is a specific purpose. You are not allowed to bring in any printed material. You can write anything by hand and you can bring it in you can write the entire book by hand. That is allowed, but you have to write it out. And you cannot photocopy also and take a photo and picture and share it with your friends. So it should be in your own handwriting. Again, the idea is that you look at the notes and you filter out the material which is important. And there's some learning and thinking involved in that whole process itself. Okay, and that's here. So that's the idea. Anyway, so go ahead. So we talked about availability. What is the maximum amount of energy that we can extract? And so that's the question for availability. We said availability again has three components: flow component, the heat transfer component, and the storage components. And these are the expressions for each of these three components of availability. And then we said that based on the availability, we can define a second law of efficiency, which is typically larger than the first law of efficiency. And instead of dividing work by work, here we're dividing work by availability. So how much of available work which is there is being extracted out is essentially how this expression should be viewed. Earlier, we were viewing that as what is the actual work which we are getting out of, divided by if the process was isentropic. But of course, isentropic was ideal, or it's like never going to happen. So it's like that is a fictitious thing. So we are comparing a quantity with a fictitious quantity, and that is how we were defining an ideal. There's first law of efficiency. Here, when we are defining it as work which has been actually done with respect to whatever is the potential for the work to be done. And we said that availability is very important because there is a lot of availability in atmosphere and ocean. A lot of very little of that can be actually converted into useful work. And then we went in for Exergy balance. And we said that Exergy defined in this way, taking a time derivative, and then these time derivatives which appear, this is your total energy, this is total entropy, and this is mass. We have separate equations for these. This is from mass conservation. This is, we can find it from this energy from our first law, and of course this total entropy from our second law. So once we substitute these, we get an expression which is given like this. This is my Exergy balance equation, which in form, which has a very similar form to the work availability equation. And so it has all these three components: transfer by heat, transfer flow, and transfer by work. This is the new thing which is appearing now. And otherwise, there is an Exergy destruction term. It's a growth or it's like a birth and a death term, but we are calling it as a destruction because the sign which comes before that is naturally a negative sign. So that's why it's, and we can write out this equation in words as the rate of Exergy storage, d phi dt. Storage term is transfer by heat. So this is a transfer term, and of course this is primarily because of heat. And you can see that the two temperatures at which heat is getting added and the surrounding temperature are different, which is what is leading to this Exergy storage. Plus transfer of shaft or slash boundary work. So you can see that this is my shaft work, or the work which can be done by my control volume, which is happening because of the expansion. This is a PdV work. This is happening at the boundary, plus the transfer of by flow. So you can see that these terms are bringing in the mass, taking out the mass. And of course, when bringing the mass, the Exergy is going to increase, or any quantity increases, and taking out reduces that. So this comes with a positive and a negative sign. And then the last term is my destruction term. And we see that these three are my transfer terms, and this is my Exergy destruction term, is because if you were to it out for the surrounding as well, then you will have the same appearing, but these terms would come with the opposite sign. So these terms, when you add up the two, these terms will cancel out, and that's why they are transfer term. They're getting transferred from your system to the from your surrounding to the system, vice versa. And then, but this term remains. So this is your source term. So this will always be a negative in this case. Exergy will always destroy itself and will reduce with time. And just like entropy, this is not a physical quantity. This is not something that we can either physically measure or we can physically relate to. This is just, so you can see that entropy in the way that we have introduced comes because of our, where does it come from? How did the entropy come about in the way that we have defined things? Anybody recalls? Or we are too far away from that lecture?
Sir, could you repeat the
Sir,
question?
So the question that I'm asking is, how did we, in our line of arguments, how did entropy show up?
from the Clausius inequality?
Yes, that's right, exactly. So it showed up from the Clausius inequality. Okay, so we showed it that it comes because we did the quantity delta Q upon T, which is always going to be positive, and then positive greater than equal to zero, or was it less than zero? So I'm sorry, I'm missing the sign here. So it's coming from the Clausius inequality, and from there we could define the entropy. Okay, so that's how it shows up. It was delta Q upon T is less than, over a cycle, was turning out to be less than equal to zero. So that's where we introduce, that's how we introduce the entropy. So that's in our line of argument, that's how entropy shows up. And once entropy shows up, you can see that availability is showing up because of this expression here. Okay. This is, of course, a combination of these entropies and internal energy, or energy, and your PV work. Okay, and you can see that these are all properties. This is something that I had not emphasized earlier enough. So these are all in terms of properties that we're defining, and therefore this phi is also a property. And the last thing that I would like to mention here very briefly is that you see these terms U minus Ts appearing. E minus Ts, E is of course U plus the kinetic energy and the potential energy term. So you can see that this term U minus Ts appears at so many places, and therefore these are given a special name, sometimes known as Helmholtz and the Gibbs function. So U minus Ts becomes my Helmholtz function, and H minus Ts becomes my Gibbs function. Okay, so these are all related to your availability, or the free energy, sometimes it's known as the free energy. So you can see that it's only that part of energy that can be converted into work. Okay, so these are all going to be used for computing the reversible work. Okay, so I'm just very quickly introducing this because they are and I would like you to know about it, although in the previous class we did not have time to cover this material. So any questions before we move ahead?
Sir, can you please explain once the difference between the second law efficiency and first law efficiency?
Okay, so the first law efficiency was defined in terms of the actual work. This is for a turbine. You can do it for other components as well. So for a turbine, the actual work which is being extracted by the turbine divided by if we were to conduct an isentropic process, okay, then how much work I would extract. So those two, the ratio of those two, the actual work to the ideal work would be the amount of work that would be my efficiency. Whereas in this case, the way we are defining it is the work which has been actually extracted by what is the work. Okay, so that's the difference.
Sir, is
Yeah.
there in this equation there is phi? Are these corresponding to a flow rate work?
Sorry, can you just repeat your question?
In the second law efficiency equation, in the denominator we have phi's for inlet and outlet. So are these corresponding towards flow rate work?
Yeah, so you can see that these are, yes. So this is going back to your midterm question. You saw that there was a stream which was coming in and the stream which was going out. Okay, so essentially the availability has to be calculated that way. And you saw that there the potential energy changes and the kinetic energy changes were not very significant. Okay, so of course, otherwise you will have to, so this is going to be a definition which is going to be customized for each of these quantities, but the general idea or the general way that we are defining will remain the same, which is the work which is being done divided by the availability that we have. So if we were to define it by with respect to pump, it would essentially become somewhat just like in the pump, we said that the isentropic work divided by the actual work. In the pump, for the case of a pump, it gets inverted. So you can see that you can define a second law efficiency for the other components of the devices that we would have in a similar manner, essentially based on, again, availabilities. So I just want you to understand that there is something like a second law efficiency. And so as we were saying that this is comparing yourself. So if you can work for 16 hours a day and you are only working 8 hours a day, your efficiency is like, as per this, is like 50%. In the other case, you are saying that this is how much I'm working and this is how much my friend is working. And my friend is the ideal one. I would like to follow him. And, uh, and therefore, this is my efficiency. So you can see that that's the basic difference in the two scenarios. That's there. So in one case, you're comparing the same quantity, as we said, work with work, and here you're comparing work with your availability. But you're comparing at the same points. In the other case, you're comparing the same quantities, W and W.
Sir, so here is the psi, the Gibbs function that we just described.
Yeah, so it will become that, yes. So
Okay.
I'm just giving you this name so that although you have seen this quantity, Q minus Ts and H minus Ts, when you see Gibbs function, you should not say, oh, we never saw this in our thermodynamics course, okay? So in some sense, you know all these concepts already. It's just that sometimes it is useful to know these names as well. Okay, so I think we'll have time to just introduce this topic. Yeah, okay, go ahead.
So can you explain again what exergy is? Like, what is the physical meaning of exergy? I'm
So
not
as I
quite
said,
sure.
entropy and entropy, these are all like irrational quantities. They can't measure. These are not like physical quantities. Even, for that matter, what is energy? What is momentum?
Yeah, okay.
Okay, it's like a quantity like that. Okay, momentum. I mean, uh, if once you are seeing it for the first time, it's like very, very abstract. It's just that you keep seeing momentum. You say, oh, momentum is just okay. To you, kinetic energy is half mu square, right? You just get so used to it. You say, oh, yeah, that's okay. It's just energy. But what exactly it is? Okay, you say that this body in front of you has this pen that you are holding has some energy. What is that now? So it's just a very abstract quantity. It's just like same thing with entropy and exergy and anything else. These are all very abstract things. It's just that again, you cannot. Can you measure energy directly? No, you can only measure indirectly. You can only measure like velocity or position and whatever forces etc. acting, and then based on that you can say this is my energy. Right? So it's again a drive quantity. It's not something that you directly measure. It's not like you connect a thermometer and you say this is my temperature, or you connect a barometer or and you say that this is my pressure. Right? So it's not like you can measure something directly. Okay, but once you have measured certain quantities, you can multiply or divide and do some mathematical operation, and then you will get your energy. Okay, so we will introduce the idea of. So I will maybe, because I want to introduce, we will skip this slide and do it in the next class. But what we would like to do is we would like to understand a power plant. So this is something that we had said in the very beginning. And now we are going to introduce some cycles, some useful cycles, primarily two cycles that we will introduce. One is how do we extract power in an actual case. Okay. So from that will lead us to the idea of Rankine cycle. And we will also be talking about a refrigerator. So we have been talking about a heat engine and we have been talking about a refrigerator. So I will introduce these two cycles now. And so you will see that all the ideas that you have been talking about, we have been talking about as part of this course will come together conceptually at least. Calculation wise, it will be much simpler than what we have seen. But conceptually, all that will come together here. So let me introduce this cycle first, the Rankine cycle. So the axis on which this has been plotted is a TS, temperature, entropy axis are the two axes that you see here. You see this dome. This dome is by now you should recognize as this two-phase region. So on the left-hand side, you would have your liquid phase. On the right-hand side, you have your vapor phase. And you are operating things in between. So you can see that this cycle is operating primarily in the two-phase region. You tend to leave this two-phase region a little bit here, okay, when you go into the liquid side. And then otherwise, you are primarily inside this dome. We'll see that we would normally, this is we are introducing, we are inside the dome, but most of the time we would actually go a little bit on the vapor side as well. But of course, most of the time we are inside this state in the two-phase region. Now, how the way this cycle starts, we can start off from 1, go to 2, and so on. So again, to remind you that these lines are at constant pressure. These are your constant pressure lines that we see here. I'm just pointing it with my cursor here, so you should be able to please follow it on the screen. So these lines are your constant pressure line. And as you go towards the top, the pressure is larger. So this corresponds to a larger pressure line. This is at a smaller pressure line and so on. So you can see when you start from 1 to 2, you are in the liquid region and you are going from one pressure to a higher pressure. Okay, so you are actually increasing the increasing the pressure for which you'll have to do work. And this work in the liquid region will be done through a pump. Then from 2, you add heating, adding heat. So you can see that your pressure increases and then you start boiling. You start moving along this line. And then once you start having a phase change, your liquid is changing into vapor, your pressure stops, the pressure is not changing, your temperature is not changing, both of them are constant. So you move along a horizontal line because the temperature is constant and it's a TS diagram that you are looking at. And the pressure line is also parallel to the entropy axis that we know by now. So both pressure and constant are along this line and you move from 2' to 3 along this axis. So you can see from 2 to 2' and then to 3, this all corresponds to heat addition. So just like in a Carnot cycle, you have a heat addition part of your cycle, and this is happening between 2' and then 3. And then from 3 to 4, you are doing all this heating, etc., because you would like to extract the work. So this is the part where you extract work from 3 to 4. You take this high pressure and high temperature. So you can see that you have, by heating, you have moved from this state to this state. Your temperature has increased. It's obvious because on the vertical axis is temperature. Your temperature has increased, and also from this pressure to this pressure is you have increased your pressure. So you are now going from a higher pressure. So you have high pressure, high temperature steam with you, and you would like to utilize that energy that you have to run a turbine. So that's why, and so you pass this steam through a turbine, and your state changes from 3 to 4, from a high pressure, high temperature to a low pressure, low temperature. Okay, so this is the most useful part of your cycle where you're extracting work, okay, which is 3 to 4. And then from 4 to 1, you know that we cannot complete a cycle without rejecting heat. So this is your heat rejection part. So 4 to 1, you reject your heat, and then you can repeat this cycle. Okay, so this is how a Rankine cycle operates, and this is how a power plant cycle is idealized. Okay, so this is a Rankine cycle which I wanted to quickly introduce, and then we will come back in the next class and we will see how this cycle compares against a Carnot cycle. This is what we'll do in this slide, and then we will see how much work and how can we increase the work which is possible from a Rankine cycle by either changing the pressure or changing the temperature and then moving ahead. So in some sense, the most important part of this chapter is to understand this Rankine cycle, how it is operated, and then be able to do calculations based on this cycle. Okay, and find out how much work is being done by this cycle. So earlier we had been looking at only this part or some other part, heat addition part, or so we had looking at these various arms, but then we will in this chapter, we will combine all this and we should be able to do the entire cycle. How do we complete entire cycle? So I think this is what we have for today. And let me see if there are questions here.